Hi folks, and welcome back to Physics with Captain Rod. I'm making this video to be just kind of an introductory video on the concepts of how to analyze a one-dimensional gravitational acceleration type problem. You know, your standard rock thrown in the air or watch dropped off a bridge or that kind of problem. So first of all, let's talk about what we're looking at over here. So we've got my favorite physics person here, Timmy. And we're going to imagine that Timmy drops this basketball. Now we're going to imagine he doesn't throw it up or down, left or right, just drops it off of this building. Now, when you're working problems in physics, always start with a good picture. So this is just kind of a start of the picture. Now label all of the relevant data in the picture. So this basketball is starting some height off the ground. Now, I'm just going to call that h for now, but if you had a number, I would label it h equals whatever that number is. Now we also want to show graphically that what the motion of that ball is going to look like. So it's accelerating down. So if we do the motion diagram, and just a little quick reminder, remember the snapshots in time. Like I always think of a digital camera going click, 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 and then superimposing all of the pictures. Right? This ball will accelerate down. That acceleration is what we call the free fall acceleration, or the acceleration due to gravity. The numerical value of that is approximately 9.8 meter per second, or 32 foot per second in English units. Now these come with a couple of assumptions here. These are true for objects that are relatively heavy compared to their surface area. So this basketball over a small distance, we can probably apply that to it, or a rock, or let's talk about what you don't apply it to. So if you were to drop a beach ball, something that's really large and has a lot of surface area, air drag would be too big a factor. Its acceleration wouldn't be near this, or a tissue paper, things of this nature. But as long as we're talking about a rock or a cell phone or your keys, something that's reasonably heavy compared to its surface area, the numerical value of the acceleration, pretty well anywhere on the surface of the Earth, will be one of these two numbers until that object reaches speed where air drag is significant, but I'll save that for another video. So we're just going to assume for now that this ball will accelerate down at about 9.8 meter per second. So we have our motion diagram showing the distances between the ball increasing with time. All right. Now, after you get your picture, then you choose a set of coordinates to work in. Now, I've already drawn a coordinate system over here, right here. And how you orient the coordinate system is entirely up to you. So I'm in the habit of doing something like this. I usually, I like to align most of the problems so at t equals 0, the x and y coordinates, if relevant, are both 0. So if you want, I've got an important thing to realize. Right now, the way I have this, the y coordinate, the positive direction is pointed up. If you don't like that, you are completely free to turn these coordinate systems around. Oops. And it might look something like this. And you would just get rid of the x coordinate, and now the positive y coordinate, or the y coordinate of that ball, will be positive the entire time. Now, because I think it just works better, especially when you start talking about projectiles, and that's usually next in my classes, so I'm just going to go ahead and go back to this one, because this is the one I use for projectile motion. And before I move it over there, I'm just going to get rid of the x coordinate here, because we don't need it. Oops. So I'm going to use y to represent the coordinate of that ball. And go ahead and put this right here. Now, some common coordinate system choices, by the way. If we put the coordinate system here, our initial y coordinate would be 0. Another common choice might be to put the 0 on the ground, in which case the initial y coordinate of the ball will be whatever h is. But again, I'm going to go back and put my 0 here. Now again, where that 0 is entirely up to you. Now don't mistake this, by the way, for a any sort of like vector that's not a velocity vector pointing up or anything like that. In fact, I might even, let's just move this over. There we go. The x coordinate of the ball doesn't matter, and the ball is now still starting at y equals 0. Now, the idea is how to kind of understand these graphs. So I'm going to use y to represent the position of the ball, v to represent the velocity of the ball, and a to represent the acceleration of the ball. Usually with these problems, you typically start with the acceleration graphs. So this ball accelerates down at a value equal to about 9.8 meter per second per second. And if we ignore air drag, that acceleration would be constant. So in the set of coordinates, we'd be coming down here to 0 and negative 9.8. And I'll just put the units over here, meter per second squared. So this is our way of saying that the acceleration we believe is down. That's the fact that that's negative means opposite of what we're calling positive. Now, as time goes on, like maybe a second later or so, we would believe that, the acceleration is still negative 9.8, assuming it hasn't hit the ground yet. A second later, still negative 9.8. So very important to realize that if we believe the acceleration to not be changing, this graph would be horizontal. Now, if we knew a time, you could put a time there. A very common thing that I like to do here is I'm just going to put a t here, where this, could be any numerical value. So there's my graph describing acceleration against time. Now we'll go up and talk about the velocity graph. Now remember, in this example, Timmy dropped the ball. So under those circumstances, we would expect the velocity at t equals 0 to be 0. Now, had Timmy thrown the ball straight up in the air first, maybe, so it did something like this, then that first point would be up here somewhere, because the ball would have some initial velocity in what we're calling the positive direction. Had Timmy thrown the ball down first, we would have an initial velocity that's downward, or in other words, some negative initial velocity. This graph would start down here somewhere. But sticking to the example at hand, assuming Timmy just leaves that ball or lets it go from rest, we would assume at t equals 0, that graph would start here. Now, a second later, we would expect the velocity to be about negative 9.8 meter per second, negative 9.8 meter per second. Here's why. The acceleration, which we believe is negative 9.8 meter per second squared, is equal to change in v over change in t. So if this, getting used to a new pen here, if this were 1 second, the delta v would equal negative 9.8, meaning that if 1 second goes by, we would expect a velocity to be negative 9.8 meter per second. After another second, negative 19.6, and so forth. So this graph is going to look something like this. I'm just going to carry it out to the same time here. Let's talk minus signs again. Very important to understand how this works, right? Remember, our original coordinates here are assigning up to be positive. Well, the ball's accelerating down. That's why the acceleration is negative 9.8. The actual meaning or interpretation of that minus sign is opposite. It doesn't directly mean down. It means opposite of what we're calling positive. The velocities also point down, and that's why they're negative, because the velocities are opposite of what we're calling positive. This graph we would expect to be linear, because if we assume constant acceleration, and remember that your acceleration is your slope of a velocity against time graph. All right, let's move on and talk about the position graph. So, right, we look right here, and at t equals 0, the y-coordinate of the ball is 0. Now you'll notice, like a second later, the y-coordinate, and we're down below our 0, so it's some negative number. Some small negative number I'd like to add, because this has not fallen far yet. But here's the important thing. The next delta t the ball falls further, meaning that the delta y is a little bit larger. So the next second, this has now done something like this. Next second, something like this. So this graph is going to have some curvature to it. So here are the three graphs, and again, this is meant to be just an introductory video here on how to analyze motion. I'm going to save the how to write the equations for another video. But for right now, for this ball being dropped off the building, our acceleration graphs, velocity graph, and position graph, these are what these would look like. And you have to understand kind of how to draw the graphs, really, I think, before you start worrying about actually writing the equations and solving the problems. So again, very important factors. The plus and minus signs are all dictated by this, right? Let me go through some possible changes. If we took the positive y direction and we reversed the direction, let's talk about how that would change these graphs. Okay. The acceleration, which we believe to be 9.8 meters per second downward, would now be positive 9.8, meaning that it's in the direction we're calling positive. This graph, since the velocities are all downward in what we're calling the positive direction, these would all be positive. So this would now point up this way. And then your y coordinates would all be positive. So now this graph would go up, like so. So the important thing is that your graphs match your coordinate system. You go ahead and put that back the way it was so that my graphs match the direction that I'm defining as positive. So that's the important thing. That's what students, I think, have a little trouble with. They always want to be kind of told what's plus or what's minus. Well, the reality is, when you're looking at a physics problem, you're trying to do your homework, you choose this. This right here, you get to choose what direction's positive. And then that will dictate the signs on this stuff. Okay, and there's no wrong answer to the choice. In a question like this, you could do down positive or up positive. They're equally valid. So anyway, again, just meant to be an introductory video. I think I'll make a second video on how to write the equations. I hope that this helps. Have a great day.